And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to finish up on our conversation concerning summary statistics, continuing on for variance, looking at Chebyshev's inequality, and we'll start getting into families of distributions. But before we begin, some administrative bits. Project 2 is due this evening at 11:59 and 59 seconds, this evening being Tuesday, the 6th of October. There is new reading due by the 13th of October, section 3.3 to 3.4, pages 47 to 67. As usual, make sure you're staying up with the reading. The key to success in this course is engagement with material, and that certainly includes reading the book. Don't fall behind. All right. So when we last left off, we talked about summary statistics, and we looked at properties of variance, covariance, and expectation. And one of the things we talked about is so-called linearity of expectation. We looked at so-called affine or scalar changes. You multiply by a constant and add a constant. And in the particular case, we looked at expectation of ax plus by plus c, where x and y are random variables, a, b, and c are scalars. So this linearity property says the expectation of that transformation is a times the expectation of x plus b times the expectation of y plus the constant c. Likewise, we also talked about the variance of that affine transformation. The variance of ax plus by plus c, we demonstrated, is a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance between x and y. So why don't we jump right into Chebyshev's inequality. Now, we know various summary statistics. We talked about mean, the center of the distribution. We talked about the variance. We talked about the standard deviation. And we talked about the covariance and the correlation. And often, when you're thinking about a measurement system or random variable, it's useful to know how likely that random variable is going to take on a range of values around the mean. So you have the mean value, and this measurement, a random variable, is going to wiggle above and below our expected value, which is the mean. And so let me set my pen color here. Why don't we go with blue? Imagine if you had a measurement of temperature, and those measurements are at some time instant. Here's your first measurement. Here's your second measurement. Here's your third measurement. Here's your fourth measurement, and so forth. And let's say you have n many measurements. Now, of course, this is the time step or the measurement you've taken along a horizontal axis. And then you have the temperature, 0 degrees. And maybe this is 20 degrees. And then maybe you have 40 degrees. And then you have 60 degrees. And then you have 80 degrees, etc., 100 degrees. And now this temperature, if you are going to take the average of the temperatures throughout the day, now of course we're in early October, and let's assume that the average temperature was right about 65 degrees. And so here we're going to draw the mean, mu, is equal to 65 degrees, for example. And of course, if you measure the temperature throughout the day, maybe it's really cold at night. It's going to kind of jump up and down, and then it might go up a little bit. It might come back down, but on average, it's 65 degrees. Now, of course, one of the things you might want to wonder is how much up and down that particular temperature will range. A certain distance above the mean, we'll call that epsilon, and below the mean, we'll call that epsilon. And so you might want to know, is it likely to go outside of epsilon? So is it going to go in this range, or is it going to go maybe in that range? How likely is it to stay within this band, epsilon, above and below the mean? And so that, in essence, if you think about it, is a kind of measure of stability. If it's more stable for epsilon smaller, it's more likely that these temperatures are going to stay within that epsilon. If epsilon is much bigger, that means it's less stable. And so one of the things we might want to know in our example, how likely is it for the temperature today to be more than 20 degrees beyond the average, above or below? And the question this type of thing is asking in this example, is it way off from what we're accustomed to, right? What we're accustomed to, the expectation, probabilistic average is our mean. How likely is it to be off from something we're accustomed to? Now, this is where Chebyshev's inequality comes into play. It describes a bound, a probabilistic bound, and this bound sets limitations on how the probability that a random variable can exceed a threshold, i.e., how often it is beyond a typical value, spread away from the mean. And so how we write Chebyshev's inequality is as follows. The probability that random variable, big X, so this is random variable, that the difference between big X and its mean, so this is the mean of that random variable, that the magnitude of that difference, how much it differs, and it doesn't matter if it's above and below, so we do the absolute value, that this difference between random variable X and its mean exceeds some threshold we're calling epsilon. Now, epsilon is the number, and we have greater than, the inequality, to connote exceeds. And so we say that what's the probability that the difference between random variable X and its mean differs by more than some threshold epsilon. That probability is no more than, right? So it could be equal to or less than, but not greater than, is no more than sigma squared, the variance of that random variable divided by that epsilon. Okay, so what is that saying? Well, the biggest probability you're going to get for this exceeding between X and its mean, that difference being greater than epsilon, the greatest that probability can be is sigma squared over epsilon. Of course, it can be less than sigma squared over epsilon. It can be as small as 0, because 0 is a valid probability, and probabilities are never negative. Okay, so to make sure you understand this, we're going to kind of go through a little bit of a pictorial example, but please make sure you're reading the following portfolio construction examples in the book. That's going to be really important for this class. Now, certainly, if your instructor says it's going to be really important, you would behoove you to go ahead and review those examples and make sure you understand them, because it's going to be really important. And so these examples in the book, example 3.13, 3.14, 3.15, make sure you understand how they work. It is a Chebyshev inequality example. So we have Chebyshev's inequality. And here we have a probability distribution. On the horizontal axis, we have our values, little x, that random variable, big X, can take on. So here we have all of our different values for little x, and the mean, mu, of random variable, big X, taking on some value, little x. Mu, the mean of, or expectation of that random variable x, is right here. So I'm drawing that mu. Now, of course, when we look at this magnitude, the absolute value between random variable X, more correctly, values that random variable X can take on and its mean, that's this epsilon here. Now, because we take the absolute value, the magnitude, we're looking at epsilon above the mean and epsilon below the mean. So this point here, that's just mu minus epsilon. This point here, that's just mu plus epsilon. And so here, to say that X minus mu magnitude exceeds threshold, epsilon, greater than that threshold, that refers to this region out here to the left of mu minus epsilon, and then also refers to this region here that's to the right of mu plus epsilon. Okay, so if we were to shade this in, what it does is it bounds the probability of this red region. Now, of course, this is a distribution, this curve, and so if we were to take the integral or add up all the probabilities for that region to the left of mu minus epsilon and to the right of mu plus epsilon, that region, if we add up these probabilities, the biggest it can be is sigma squared over epsilon squared. And certainly it can be smaller. It could be as small as 0. Okay. So, of course, when you look at stocks, one of the things you're interested in is how widely a stock's value can swing. So this might be useful for looking at the volatility of some stock or security. So let's take a look at this. We're going to prove Chebyshev's inequality. And of course, I've restated it up here. And we're going to start out and we're going to write out what the variance is for our random variable X is. Because in essence, this Chebyshev's inequality, it's really a measure of dispersion. How much probability mass is outside of this region epsilon away above or beyond this mean mu. And so we write the variance, and it's just our regular variance equation, sigma squared is equal to the sum for all values. These are values, little x. It's x minus mu, quantity squared, and that's our variance. We weight that by the probability that random variable big X takes on value little x. And there's our expression for variance. So now what we're going to do, we're going to consider not all values of x. We're only going to consider those values of x that are greater than that epsilon above and below away from the mean. And so here is my epsilon distance away from the mean below, and here is my epsilon distance above the mean. And so when we say not just any x we're summing together when we compute the variance, we say the variance of those x values or measurements that are outside of this epsilon region. Well, if we add up the variance, well, that's variance here, and that's variance of this portion. Let me kind of shade those in. That's not all of the points that contribute to variance. So let's look at what this variance is doing. We say x minus mu, and we square that. So this is always positive. And the probability, it's always 0 or positive. So if we have terms here, additional terms in our summation for terms of the variance, they're always positive. So that means if you include more points here for x in the variance calculation, it's going to be bigger. If you include less points, it's going to be smaller. So what does that mean? We can rewrite this expression and say, let's not just consider the variance for all of the measurements x. We're only going to consider the variance or the components of variance contributed by those points that are beyond epsilon above and below the mean here. And so if we do that, we're excluding other points that are within that epsilon above and below the mean, right? And so if we're excluding those values, that the resulting variance is going to be smaller. And so we know that the original variance, or the full variance, is going to be at least bigger than, greater than, equal to, that reduced variance. And that reduced variance is reduced because it only considers those values x that are outside of that epsilon above and below the mean. And so we write this expression, our original variance is greater than equal to, and you can pronounce this at least, is at least the variance due to those points that are outside of this epsilon region above and below the mean. And so this is absolutely true. As long as we satisfy this mathematically, we can absolutely state this, and this is absolutely true. Okay, so now that we've written this reduced variance, we're going to go ahead and we're now going to replace x minus mu with exactly epsilon. Now here we see this probability. It says x minus mu greater than epsilon. So that means x minus mu, the magnitude, whether it's above or below, that value is always greater than epsilon. So if you have something that's greater than epsilon and you square it, if you replace it with epsilon, well, the value that we get is always going to be smaller because epsilon is smaller. So now we're squaring something, and then we're replacing it with something that's smaller that we're squaring, so the result is going to be smaller. So if we replace this x minus mu with epsilon, we're going to use the inequality greater than equal to, because this expression, x minus mu, is greater than epsilon. So if we replace with epsilon, this resulting term is going to be greater than equal to the version involving epsilon. So we replace that with the sum for our restricted x values. And we've also replaced this with epsilon instead of our x minus mu. And we write our restricted sum, epsilon squared times probability of x. So this is just a straight replacement, and this inequality, at least or greater than equal to, acknowledges the fact that this epsilon is less than x minus mu, that difference between x and its mean. All right, so now we're going to clean this expression up a little bit. We make the observation that this epsilon here, it does not involve x, and for all intents and purposes, it is a constant underneath the summation. The summation index is values little x. Now, of course, we can pull this out, make use of the distributive rule, distribution of multiplication over addition in reverse, and we factor out this epsilon. And so that is exactly equal to epsilon squared times our summation for each of those x's outside of the epsilon region above and below the mean. And we have probability of big X, random variable X. Okay, so now if we consider what the sum is, that sum is nothing more than all of the places where x minus mu is greater than epsilon. So we're just going to make that replacement for that probability. It's a cumulative probability, and it's a probability that x minus mu is going to be greater than epsilon. And that looks at those two regions on the tails that we alluded to before, where this one is at position mu minus epsilon, and then this other one is at position mu plus epsilon, and then here we have mu in the center. Now, of course, if we take the summation, we're summing over all the probabilities associated with all of the x values for this region below mu minus epsilon, and this region above mu plus epsilon. That's nothing more than this probability. The probability that x minus mu absolute value is greater than epsilon. Okay, so now if we do that, well, we're going to gather together all these steps here. So we have sigma squared is equal to, is greater something, is greater than equal to, is greater than equal to, is equal to, is equal to. So if we were to rewrite this, we'd say sigma squared is equal to something that's greater than equal to something that's greater than equal to something that's equal to something that's equal to epsilon squared probability x minus mu greater than epsilon. So we can rewrite this compactly, keeping in mind all of the inequalities here, and write this as sigma squared is greater than equal to epsilon squared probability of x minus mu greater than epsilon. Okay, so we do that, and we get this expression. Sigma squared is greater than equal to, or at least, epsilon squared probability, the difference that x minus x exceeds mu by more than epsilon. And we can rewrite this. You'll notice it's from left to right, but we can write it from right to left. So if I say sigma squared greater than equal to epsilon squared probability of x minus mu greater than epsilon, I can also write that as epsilon squared probability of is less than equal to sigma squared. So I do that, rewriting from right to left instead of left to right. I get epsilon squared times probability that x exceeds mu by more than threshold epsilon, or tolerance epsilon, is at most or less than equal to sigma squared. So now, do a little algebra. I can divide both sides of this inequality by epsilon squared. So if I divide this by epsilon squared, divide that by epsilon squared, I get this side goes to 1, because I have epsilon squared in the numerator and denominator. That leaves probability that x exceeds mu by more than some threshold epsilon is at most less than equal to sigma squared over epsilon squared. And so there's my result, but I'm not quite done yet. I can actually group together the numerator and denominator and square it after the fact. And so that probability that x exceeds mu by more than threshold epsilon, the magnitude of it, is no more than, or at most, sigma over epsilon quantity squared. All right. So this gives us an upper bound on the probability, which is the upper bound on the probability of this red region, and it gives us a way of measuring this notion of what is typical. Now, of course, if epsilon is really large, that means x is going to vary a lot more. If epsilon is really small, that means x is not going to vary as much. And so if epsilon is large, well, what happens? You have a lot of variability, and the probability that you exceed the threshold epsilon is going to be smaller because the threshold is larger. If the threshold is smaller, well, what happens? You have a small threshold. That means the probability is going to be much greater that you're going to exceed, and because your tolerance is less. So it kind of works the way you'd think it would, and it's a great way, just Chebyshev's inequality, to talk about the wiggliness or how typical a measurement will be. And you can do that based on this idea of a tolerance. Okay, so let's transition to distributions. And certainly, we talked more generally about a distribution in table format, and then we showed in graph format how you can talk about a distribution, and we said it describes the aboutness of your system, the data or the values that are measured. And then we talked about summary statistics over these distributions, and then lastly, most recently, the wiggliness using Chebyshev's inequality. But certainly, you'll notice that certain problems look a lot like other problems. If you're trying to choose, for example, males or females on a co-ed soccer team, it's the same as flipping a coin. And this observation, a lot of people have made over decades. A lot of researchers and mathematicians, statisticians in particular, have studied lots of different systems and the distributions that governs the measurements from those systems. And so to make things easier, they developed functions that kind of are common to certain ways that things vary, stochasticity, or this when can I see you again. So they develop these functions. Then these functions play a role in making the description of the distribution a lot easier. Now, these descriptions are widely applicable to systems that share properties in terms of the aboutness of their data or the variability that is seen in the data. And so this can talk about system properties, these functions, these descriptors. It can be functional descriptions about how something proceeds over time or how that function behaves. And so this begets this notion of a quote-unquote family of distributions. And there are two types of families of distributions. There are so-called discrete distributions, and these are distributions for random variables whose collection of measurements that random variable can take on is either finite or countably infinite. And then you have so-called continuous distributions, and these are distributions whose random variables or measurements are uncountably infinite. They're so-called continuous. And of course, the difference lies in how you add up probabilities to compute complex events. In the discrete case, we use summation. In the continuous case, we use the integral. So let's talk about our first distribution. One is called the Bernoulli distribution, and this is the simplest one. It's a random variable that can take on one of two possible values. So our sample space omega is going to have a cardinality of 2. This could be examples of this include flipping a coin. You have heads or tails, or picking a co-ed team consisting of females and males. Now, a random variable that takes on one or two different values, you could call it A or B, you could call it plus or minus, but in the book, they call it success or failure. Now, this type of random variable that can assume two values, so its range is going to have cardinality 2, is called a Bernoulli random variable or Bernoulli variable. And therefore, the distribution of such a random variable is called a Bernoulli distribution. And so this experiment that gave you these two observations, success or failure, the experiment that gave it to you is called a Bernoulli trial. It's named after Jacob Bernoulli, who was a mathematician that developed it. And so let's look at the Bernoulli distribution. And let's call success, the probability of success, or the success date, we'll call that the 1 event. And then we'll call the failure event the 0 event. So the probability of success is called P, and it's some probability. It doesn't matter what it is. It's between 0 and 1 on the real number line. And then the converse of P is Q. That's the probability of failure. And by law of total probability, that's just 1 minus the probability of success. Because there are two alternatives, we know that Q plus P is equal to 1. And so let's look at the expectation of a Bernoulli variable. So E of x, where x is a Bernoulli random variable, is for all instantiations of random variable x. We'll call that little x, and that's our loop index. So here's the value. And then here we have the random variable taken on the value. So there's a value weighted by the probability that that random variable big X is going to take on that value. So this is our probabilistic weighted sum, and we're going to use what we have before to compute the expectation, which is the mean of this Bernoulli distribution. And so here, whenever X is success or 1, that occurs with probability 2, so we multiply 1 times P. And then whenever we have failure, that's probability Q, we have 0 or value times 1 minus P, which is what our Q is. Now, Q is just another name for 1 minus P. It's a convenience to say Q instead of 1 minus P. So we add the two together. That's 0 plus 1 times P. That's just P. So P is the probability of success for a Bernoulli random variable, and the expectation of a Bernoulli distribution is just P. All right. So let's now take a look at the variance. And so here's the variance equation. Now we're going to compute the summary statistic variance for a Bernoulli distribution. And so that's our setup for variance. It's just each measurement x, all right, with sum over the difference between each random variable's value x, little x, and its expectation E of x. Now we just said that E of x, our expectation is mu, right? So we're going to use that fact that E of x is mu in this solution. So we're going to take this difference, we square it because we care about the magnitude, not the direction, for variance, and then we're going to weight it by the probability. Now, of course, if I do this out, this is nothing more than x minus mu quantity squared, and we'd use the FOIL rule to compute what this inner term is. And so if we did that, that's x squared minus 2 mu x plus mu squared. Okay, so if we do this, we expand that FOIL rule for this squared parenthesized expression, x minus E of x quantity squared, and we get the following polynomial. We have in our parentheses x squared minus 2 mu x plus mu squared, all times probability of x. Now we notice that we have multiplied by P of x times this parenthesized expression, and we're going to make use of the distributive rule, distribution of multiplication over addition, and we're going to multiply the first term by P of x, multiply the second term by P of x, and multiply the third term by P of x. So if we do this, and then we group together the individual summations, we get the sum for x squared times P of x minus 2 mu times x times P of x plus mu squared times the sum of P of x. Okay, so if we do this, we can make an observation. We say, okay, well, the sum of x times P of x, that's nothing more than mu. It's the same mu as what's here. So if we do this, we replace this term with mu, that summation, and then we have mu squared times the sum of P of x. Well, the law of total probability says we sum over all values of the probability, that sums to 1. So that's the same as mu squared times 1. So we're left with the sum for x squared times P of x. That hasn't changed. That's exactly what's up here. We say 2 mu times mu. Okay, that hasn't changed. We did this reduction. X times P of x, our summation is mu x, is mu. So it's 2 mu mu plus x squared times mu squared, rather, plus mu squared times 1. All right, so that mu squared here is there. There's a mu squared, and 1 is just this total probability, the summation of P of x over instantiations, all instantiations of x. Okay, so now when we do this, we make an observation. Well, this term, that's minus 2 mu mu, so that's 2 mu squared, plus mu squared. We have minus 2 mu squared plus mu squared. That's just minus 2 plus 1. That's just a minus mu squared. And so this expression turns into minus mu squared, and we're left with the sum for all x x squared times p of x minus mu squared. Okay, so if we do this, well, there's our expression. So now that we've combined the minus 2 mu squared and the plus mu squared, we get this expression. And so now let's substitute in all of the values for failure and for success. Failure, we said, was, set to blue. So now that we've combined our minus 2 mu squared and plus mu squared, we get the following expression, the sum for all x squared times p of x minus mu squared. Okay, so now that we've done that, well, let's take a look at this. We have this first term here, this sum for all x squared p of x, and then we have this minus the second term. So let's evaluate this first term, instantiating all those values of x, success and failure. 0 is failure, success is 1. So let's take the failure case. We have 0 squared, and the probability of failure is q, or 1 minus p. Okay, so let's take the success case. So for success, x is 1, so that's 1 squared, and the probability of success, that's p, so times p, right? All right, so now we have that minus mu squared. Well, mu is p, so that's minus p squared. Okay, so now if we look at this expression, well, we have 0 times this, that's going to be 0. We have 1 times p, so that's just p minus p squared. So we take this p minus p squared, and we're going to factor out p, so that's p factored out times 1 minus p, which is just p times q. So we have this expression, substituting for x equals 0, x equals 1, and then we reduce and we factor. And 1 minus p is also what we're calling q. So we have pq. So the variance of a Bernoulli random variable, or Bernoulli distribution for that random variable, is going to be pq. And these are our summary statistics. We have the mean, mu, is equal to p, and we have the variance, sigma squared, is equal to pq. So whenever you have a problem that is structured as a two-way outcome with some probability for one of the outcomes, we'll call it success, and another probability, 1 minus p, for the non-success, the other outcome, well, the mean is just p, and the variance, sigma squared, is just pq. All right, so let's take a look at this next distribution, the so-called binomial distribution. And with the binomial distribution, we're going to perform some number of Bernoulli trials, like flipping a coin n many times, like picking either male or female n many times for a team of n people. And so if we consider the outcome of our Bernoulli trial to be a 1 or 0, 1 for success, 0 for failure, or alternative A and alternative B, this is going to give us a string of binary observations. So we're going to have success or failure for the first outcome, or of the first Bernoulli trial. For the second, we're going to have success or failure, 0 or 1, up to and including the nth, we're going to have a 0 or 1. So essentially, one of the things we're doing with this binomial distribution is putting together a number of Bernoulli trials, specifically n many. So one of the probabilities that we're interested in here is how many times did we get success out of this sequence of n many trials, n many picks. And so that's like saying, if I pick a team of n people, what's the probability that I have some number of women that I picked? And so the probability, in this case, for this so-called binomial distribution is equal to n choose x. And what that means is, out of those n trials, we're going to choose x many of them to be a success. And then that means the remaining n minus x are going to be failures. Now, of course, we say n choose x because it can be all possible combinations. How many ways can you choose x of these n trials to be the success outcome? So we say n choose x times, once you have these x, the probability of success. So if you have success, 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 x many times, well, the probability of the first success, that's this p. Second success, that's just p. That's just p times p. Each one is independent, right? The outcome of one trial doesn't impact the outcome of another. So you have p times p times p times p, x many times, that's just p to the x. Lastly, for your n minus x failures, well, probability of a failure is just failure, 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 n minus x many times. So that's just 1 minus p times 1 minus p times 1 minus p multiplied by itself, n minus x many times. That's just 1 minus p to the n minus x power. Or if you substitute 1 minus p as q, that's just q to the n minus x power. And so you put them all together, the number of arrangements you can have, n choose x, the probability associated with all the successes, p to the x, times the probability associated with all the fails, or the other alternative, that's q to the n minus x. And this is your probability mass function, the so-called binomial distribution. And so this binomial distribution can be used for any system that exhibits the same properties, a number of independent trials, each of which can be a 1 or a 0, or a choice A or choice B outcome, like male or female, or choosing chocolate or vanilla ice cream, and each trial is independent. So you have 2 different alternatives and many independent trials. You have a string of alternatives. The probability of having one alternative, the success alternative, is just n choose x times p to the x times q to the n minus x. And that is the probability mass function of our so-called binomial distribution. All right, so we also can compute the summary statistics for the expectation, mu, of a binomial distribution. That's just n times p. And the variance, sigma squared, of our binomial distribution, that's just n times pq. And I'll leave this to you in the book to work out these summary statistics. Please make sure you are working out the math for these. It's a very straightforward proof to demonstrate. So with that, that's all I had. And as usual, please make sure you're keeping up with the reading. I look forward to your Project 2 submissions this evening on the Blackboard, this evening being the 6th of October. And as usual, please stay healthy, stay safe, and I will see you Thursday.